In the previous episode, we followed the thin boundaries that keep oil inside a machine and contamination outside. Some of those boundaries depend on pressure from the fluid itself. Others rely on an elastomer being squeezed into a groove. A rotating shaft seal may include a small circular garter spring that keeps its flexible lip against the shaft. A mechanical seal may hide several coil springs behind one sliding face, maintaining contact as the faces wear, move, and change temperature. The spring is often almost invisible. It sits behind the part we notice, quietly pushing, pulling, twisting, or returning something toward a chosen position. Imagine one of those mechanical seal springs compressed by a fraction of an inch. Nothing appears to be moving. The coils are still. The steel is not producing sound. Yet the material is holding energy and applying force. If the seal face moves away slightly, the spring follows it. If the face wears, the spring extends. If vibration disturbs the assembly, the spring helps restore contact. The spring does not create energy from nothing. It stores work that was placed into it during assembly or motion, then releases some of that work as it returns toward its original shape. A spring may close a valve, support a vehicle, regulate a clock, measure a load, operate a switch, cushion an impact, maintain electrical contact, or keep a chain tensioner against a moving guide. It may be a coil of wire, a curved leaf, a twisted bar, a thin disc, a spiral ribbon, a wave of flat metal, a chamber of compressed air, or a piece of rubber shaped to flex in a controlled way. The finished object can be simple enough to fit beneath a button. The engineering behind it is not. A useful spring must deform enough to do work without crossing too far into permanent deformation. It must repeat the same movement without losing force. It must survive surface defects, corrosion, heat, vibration, and millions of stress cycles. It may need to remain flexible at low temperature, resist relaxation at high temperature, or fit into a space barely larger than the part it moves. The central tension inside every spring is easy to state. It must change shape, and it must remember how to return. The history of springs begins long before coiled steel wire. It begins with bent wood, twisted fibers, flexible bronze, and the observation that some materials push back when we deform them. Over centuries, that observation became a measured law. Craft steel became spring steel. Carriage suspension became vehicle suspension. Clock springs became valve springs. Instrument springs, contact springs, and microscopic flexures made inside electronic devices. Tonight, we will follow that long development by staying close to one physical question. How did people learn to store mechanical force inside a material, release it predictably, and make the same part survive the process again and again? A spring is a device that changes shape under load and produces a restoring force. That definition is broad enough to include a bow, a bent beam, a twisted bar, a compressed coil, and a rubber mount. The restoring force comes from the material's resistance to deformation. At the atomic scale, neighboring atoms occupy preferred relationships. Pull them slightly apart, push them slightly together, or force them into a new angle, and the internal bonding resists the change. Remove the load while the material remains within its elastic range, and those relationships guide the object back toward its earlier form. The word elastic does not mean soft. A hardened steel spring may feel rigid in the hand. Its useful movement can still be elastic because the strain within the steel remains small enough to recover. A rubber band is also elastic, though its molecular structure, amount of movement, temperature behavior, and energy loss differ greatly from steel. When a spring is compressed, stretched, bent, or twisted, an external force moves through a distance. That is mechanical work. Some of the work is stored as recoverable strain energy. Release the spring, and the stored energy can move another part. In a simple linear spring, force increases approximately in proportion to deflection. Push twice as far, and the spring pushes back with roughly twice the force, as long as it remains within the range for which that relationship is valid. The proportionality is called the spring rate, or spring constant. A high-rate spring requires a large change in force for a small movement. A low-rate spring moves farther under the same added load. The stored energy does not rise in simple proportion to movement. In an ideal linear spring, doubling the deflection stores about 4 times as much energy because both the force and the distance have increased. That is why a spring compressed a little farther than intended can become much more energetic than it appears. Real springs are not perfectly ideal. Their rate may change with deflection. Contact between coils, changes in geometry, material behavior, friction, and temperature can make the force curve nonlinear. Some springs are designed to become progressively stiffer. Others provide nearly constant force through part of their travel. A carefully made instrument spring may stay close to linear because measurement depends on it. Elastic behavior also has a boundary. If the stress rises too far, the material begins to yield. Remove the load and the spring does not return completely. It has taken a set. Increase the force farther, and the part may buckle, crack, or fracture. A spring designer therefore works between several limits. The spring must provide enough movement and force to be useful. Its operating stress must remain low enough for the required life. Its dimensions must fit the available space. Its natural frequency must stay away from dangerous excitation. Its material must survive the environment. The designer also distinguishes a spring from a damper. A spring stores energy and returns much of it. A damper dissipates energy, commonly as heat. If a vehicle wheel meets a bump and the suspension contains only a spring, the body can continue oscillating after the bump has passed. A shock absorber, more accurately called a damper, converts part of that motion into heat by forcing fluid through controlled passages. The spring supports and returns. The damper calms. Some materials and spring forms contain their own damping. Leaf springs lose energy through friction between leaves. Rubber shows internal hysteresis as molecular chains move and recover. Metal coil springs usually provide comparatively little damping by themselves. That distinction matters whenever a spring is expected to absorb a shock. The spring can receive the energy, but something must decide whether the energy is returned, dissipated, or shared with another part of the system. The same care applies to the word strength. A spring can be strong enough to survive one heavy load and still fail after millions of smaller loads. Repeated stress creates fatigue. The most dangerous point may be a tiny scratch or corrosion pit rather than the visibly largest part of the spring. A spring can also remain intact while losing force. At elevated temperature, the material may slowly relax. A compression spring held at one length can produce less load over time. An extension spring may lose initial tension. An elastomer can develop compression set. The absence of a visible break does not guarantee that the spring is still doing its job. In a seal, a small loss of spring force may become leakage. In an engine valve train, it may become loss of contact at speed. In an electrical switch, it may become resistance or intermittent connection. In a safety mechanism, it may change the pressure or position at which the device responds. If you enjoy these quiet journeys through the hidden mechanical world, subscribing will make the next part of the series easier to find when it arrives. For now, we can leave modern machines and move back to the earliest elastic devices, when stored mechanical energy was known through the hands long before it could be measured with a gauge. The oldest spring-like tool was probably not made from metal. A bow stores energy when its limbs bend and its string pulls them away from their resting shape. The archer supplies work while drawing the string. The bent limbs store part of that work. Release allows the limbs to return, accelerating the string and arrow. The material may be wood, horn, sinew, or a composite of several materials arranged so that one region handles tension while another handles compression. No equation was required to notice that some pieces of wood returned more strongly, some broke without warning, and some slowly lost shape after being left strung. Craft knowledge developed through selection, seasoning, shaping, and use. The bow already contained several themes that would remain central to spring engineering. Material direction mattered. Knots and defects mattered. Moisture mattered. Too much bending caused permanent damage. Repeated use could reveal weaknesses that one careful bend did not. Other early objects used elastic metal on a smaller scale. Bronze fibulae, the ancestors of the modern safety pin or brooch, appeared in many ancient cultures. By around the 9th century before the Common Era, some surviving examples clearly used a coiled or curved spring section to keep a pin pressed into a catch. The fibula did not store enough energy to move a machine. It solved a familiar practical problem. A fastening pin had to open, then return toward a closed position. The spring and the fastener were part of one object. Ancient tweezers used another simple form. A bent strip or pair of connected arms opened under finger pressure and returned when released. The metal acted as a leaf spring. The motion was small. The principle was complete. Elastic energy also appeared at a much larger scale in ancient artillery. By the 4th century before the Common Era, engineers in the Greek world had developed torsion-powered machines that used tightly twisted bundles of sinew or hair. Arms inserted into those bundles could be drawn backward, increasing twist and storing energy. When released, the bundles drove the arms forward. These devices are sometimes described as using torsion springs. That description is mechanically reasonable, but the spring was not a helical steel coil. It was an organized bundle of organic fibers working in twist. Humidity, aging, fiber quality, and adjustment affected its performance. Operators had to maintain the bundles and equalize the two sides. The machines show that spring behavior was already being engineered through material, geometry, and preload. Preload means that a spring is placed under force before the main operating movement begins. A fibula may hold its pin against the catch, even while apparently at rest. A torsion bundle is tightened before launch. A modern valve spring is compressed after installation, so it continues pressing the valve closed. Preload keeps contact, removes looseness, and defines the starting condition. It can also consume part of the spring's available stress range. Too little preload allows separation or rattle. Too much raises fatigue stress and may shorten life. Early craftspeople did not use that terminology, but they understood the behavior through adjustment. A spring that did not push firmly enough was tightened or reshaped. One that cracked was made thicker, shorter, or from another material. A fastener that opened accidentally needed more return force. A bow that followed the string and stayed bent had lost useful elasticity. The evidence from surviving objects is uneven. Wood, sinew, leather, and ordinary iron corrode or decay. Bronze ornaments survive more readily than workshop springs. A delicate strip inside a lock may disappear while the lock case remains. This makes the history of springs different from the history of large stone structures or monumental machines. Many early springs were humble parts whose importance was measured by repeated motion rather than size. As metalworking improved, springs moved deeper into locks, latches, traps, tools, and instruments. The metal strip became one of the most adaptable forms. A flat strip fixed at one end and deflected at the other is a cantilever spring. Push it aside, and bending stress develops through its thickness. One side enters tension, the other enters compression. Somewhere between them is a neutral region with much less longitudinal stress. The farther material lies from that neutral region, the greater its contribution to bending stiffness. This is why the thickness of a leaf matters so strongly. A small increase in thickness can create a large increase in stiffness, even when width and length remain unchanged. A blacksmith did not need to state the mathematical relationship to discover it. A thick latch spring was difficult to move. A long, thin spring moved easily. A sharp corner became a place where cracks began. Hammer marks and scale could weaken the surface. Early iron and steel varied widely. Carbon content was inconsistent. Slag and inclusions interrupted the metal. Heat treatment depended on the skill of the smith and the behavior of a particular piece. A strip could be hardened by heating and quenching, then tempered to reduce brittleness. Too soft, and it bent permanently. Too hard, and it snapped. The acceptable condition lay between them. Locks made this balance visible. A lock spring might push a bolt, return a lever, hold a pawl against a wheel, or keep a key mechanism in contact. It had to move many times while confined inside a small case. Because the user supplied only modest force through a key or handle, friction and spring rate mattered. A spring that was unnecessarily stiff made the lock unpleasant to operate. One that weakened could leave the mechanism uncertain. Traps and mechanical alarms used springs to hold energy until a trigger released it. Door latches used a spring to return a handle or bolt. Firemaking and hand tools used flexible strips in specialized ways. These mechanisms were still made largely through fitting. A smith or locksmith could adjust a spring by changing its curve, filing its width, reheating it, or replacing it with another strip. The spring belonged to one mechanism rather than to a standardized catalog size. This individual adjustment was practical, while machines remained few and relatively slow. It became a limitation when portable clocks required compact springs that delivered controlled energy for hours rather than one quick return movement. A weight-driven clock receives energy from gravity. A raised weight descends slowly, turning gears through a cord or chain. The arrangement can provide steady power, but it requires vertical space. A tall clock can hide a long fall. A portable clock cannot. By the middle of the 15th century, European makers had begun producing small clocks driven by coiled springs. The exact origin is obscure. Surviving evidence points toward development in Italy and other centers of clockmaking, rather than one undisputed inventor. Peter Henlein of Nuremberg became famous as an early maker of portable spring-driven timepieces, but the familiar story that he single-handedly invented the watch simplifies a broader development. The essential component was the mainspring. A strip of steel was coiled into a barrel or other confined space. Winding forced the strip into a tighter curve and stored energy through bending. As the spring unwound, it turned the clock train. This made portable timekeeping possible. It also introduced a serious problem. A wound mainspring does not normally provide constant torque from beginning to end. When tightly wound, it pulls strongly. As it unwinds, its torque declines. A clock escapement works best when the driving force remains within a useful range. Too much force increases friction and disturbance. Too little may stop the mechanism or reduce the balance's motion. Clockmakers developed several responses. One was the fusee, a cone-shaped pulley connected to the mainspring barrel by a cord or fine chain. When the spring was strongest, it pulled at the fusee's small radius. As the spring weakened, the connection moved toward the larger radius, increasing leverage. The changing geometry compensated for part of the changing spring torque. The device was not perfectly efficient or simple. It added parts, friction, height, and manufacturing difficulty. Its fine chain required extraordinary workmanship, yet it allowed an imperfect spring to drive a more consistent clock. Another response came from controlling which part of the mainspring's travel was used. A spring can behave more predictably over a limited range than when it is wound to its most tightly stressed condition and then allowed to run nearly empty. Stops and winding arrangements could keep operation away from the least useful extremes. Later improvements in spring material, barrel design, escapements, and regulation reduced dependence on the fusee in many watches. The mainspring changed more than the size of clocks. It created demand for thin steel strip with reliable elasticity, smooth surfaces, and consistent thickness. A thick region stored and released force differently from a thin region. A scratch became a fatigue origin. Poor heat treatment caused the spring to take a set or break. Rust could shorten the life of a component hidden inside a valuable instrument. The spring also revealed that a mechanism could fail even when no gear tooth was missing. A mainspring might break near its attachment. It might become permanently curved in an unhelpful way. Old lubricants could become sticky and make the spring coils cling inside the barrel. Uneven release could disturb the train. Watchmakers learned to inspect, clean, lubricate, and replace these concealed energy stores. Portable clocks introduced another spring whose task was not to power the train, but to regulate it. A balance wheel oscillates back and forth rather than rotating continuously. Its period depends on the restoring force that returns it toward the center. Early portable timekeepers used forms of balance control that were sensitive to position and motion. In the 17th century, the spiral balance spring transformed the problem. A thin spiral spring attached to the balance wheel produced a restoring torque as the wheel turned away from its neutral position. The balance and spring formed an oscillator. Christian Huygens announced a practical spiral balance spring watch in 1675. Robert Hooke disputed the priority and had explored spring-controlled balances earlier. Their claims became part of a long historical argument. The safest conclusion is not that one man alone discovered every part of the idea. Hooke investigated elasticity and spring regulation. Huygens published and realized a practical spiral balance spring system that had profound influence on watchmaking. Priority depends on how conception, experiment, communication, and successful construction are weighed. The balance spring had to be remarkably delicate. Its coils needed room to breathe without touching. Its inner and outer attachments affected symmetry. Its temperature behavior altered timekeeping. Its shape changed the way the balance accelerated and decelerated. An error almost invisible to the eye could change the daily rate of a watch. The regulator became an instrument for studying spring behavior. A clockmaker could observe whether oscillations remained regular, whether amplitude changed with mainspring force, and whether the spring returned concentrically. The spring was no longer only a store of energy. It became a timing element. That required a clearer understanding of the relationship between force and deflection. Robert Hooke's work would provide the most famous early statement. Hooke lived in a world where natural philosophy, instrument making, architecture, astronomy, and practical mechanics overlapped. He built and improved experimental devices. He studied air pumps, microscopes, clocks, structures, and the behavior of materials. Elasticity mattered across many of these subjects. A spring balance could measure force. A clock spring could regulate motion. A structural member deflected under load. A vibrating body produced a repeatable period. Hooke guarded some discoveries through anagrams, a common method of establishing priority without immediately revealing the full statement. In 1678, he published the phrase in Latin, ut tensio sic vis. It is commonly translated as the extension, so the force. In modern language, within a suitable elastic range, deformation is proportional to applied load. The statement became known as Hooke's law. The law does not mean every material and every spring remain perfectly linear through any amount of movement. It describes an approximation that can be extremely useful while the material stays within its elastic behavior and the geometry does not change too much. A helical compression spring often follows a nearly straight force deflection line through its intended range. Near coil contact, buckling, or material yielding, the relationship changes. A rubber element may show a curved response and noticeable hysteresis. A leaf spring with changing contact between leaves may have friction and a variable effective length. A conical spring can become progressively stiffer as coils touch. Hooke's law is a starting model, not permission to ignore the real spring. Its importance was that elasticity could be quantified. Suppose a known weight stretches a spring by a measured distance. Add another equal weight. If the spring is operating linearly, the additional extension is about the same. This allows a spring to become a measuring instrument. Spring balances, force gauges, pressure indicators, weighing machines, and later testing equipment all rely on a calibrated relationship between load and movement. The reading may be shown by a pointer, lever, dial, or electronic sensor that detects strain. The mechanical foundation remains a controlled elastic member. Measurement also made material comparison more systematic. Two strips could look alike, while producing different deflection under the same load. One might return perfectly, another might retain a slight bend. Repeating the load could reveal fatigue or settling. The spring could be tested rather than judged only by feel. Hooke's law also helped separate stiffness from strength. Stiffness describes how much a part deflects under load. Strength concerns how much stress it can survive before yielding or breaking. A thick piece of ordinary steel may be stiffer than a thin piece of high-strength spring steel, even though the thin spring steel can endure greater stress without permanent deformation. Geometry and material work together. This distinction would become crucial as machines grew larger. A carriage spring had to support weight while providing movement. A railway spring had to carry repeated impact. A valve spring had to move quickly without losing force. A measuring spring had to remain predictable. None of these tasks could be solved by the word steel alone. The steel itself needed to become more consistent. In the 18th century, one clockmaker's frustration with available material contributed to a major change in steelmaking. Benjamin Huntsman worked in the Sheffield region of England. He was trained as a clockmaker and became concerned with the variable quality of the steel available for fine components. Blister steel and other contemporary products could contain uneven carbon, slag, and local differences that complicated hardening and finishing. A clock spring or small tool required dependable behavior through a thin section. A hidden defect could ruin hours of careful work. During the 1740s, Huntsman developed a crucible process for producing more uniform cast steel. Selected steel was melted in closed refractory crucibles at high temperature. Complete melting allowed the material to become more homogeneous than steel that had remained partly solid during earlier processing. The molten steel could be poured into ingots and later forged or rolled. The process did not create modern alloy spring steel in one step. It did provide steel of exceptional uniformity and quality for tools, clock parts, springs, and other demanding products. Huntsman's early clock, preserved in Sheffield, contains components made from his crucible cast steel and reflects the connection between precision timekeeping and better material. The new steel initially met resistance from some local cutlers because it was harder to forge by familiar methods. Foreign customers recognized its quality, and Sheffield's steel industry expanded around the process. Better material did not eliminate heat treatment. Spring steel still needed to be shaped, hardened, and tempered appropriately. Hardening could create a strong martensitic structure, though the metallurgy would not be described in those terms until much later. Tempering reduced excessive brittleness and adjusted the balance between strength and toughness. Color provided an early guide. A polished steel surface heated in air developed oxide colors that changed with temperature. Skilled workers used these temper colors to judge treatment, though the relationship depended on surface, lighting, heating rate, and experience. A clock spring required a different condition from a chisel or knife edge. The spring had to survive bending repeatedly rather than hold the hardest possible cutting edge. Uniform steel made that balance easier to reproduce. It also supported the growth of specialized spring making. Wire could be drawn more consistently. Strip could be rolled thinner. Springs could be made in batches rather than corrected entirely one by one. The next great demand for stored elastic force did not come from a clock case. It came from roads. A carriage without suspension transfers every rut, stone, and wheel impact into its frame and passengers. The spring would become a structure that carried the vehicle while allowing the wheels and body to move relative to one another. Long before the automobile, horse-drawn vehicles used leather straps, flexible wooden members, and metal springs to separate the body from the harshest road motion. Leather thoroughbraces suspended some coach bodies between supports. They provided movement and isolation, though with limited guidance and a characteristic swaying ride. Steel leaf springs offered a more compact and controllable alternative. A simple leaf spring is a curved strip supported at one or more points. Load changes its curvature. Remove the load and the strip attempts to recover. Carriage builders used several arrangements, including C-shaped springs, side springs, and laminated constructions. In a laminated spring, several leaves of different lengths are stacked together. The longest leaf connects to the vehicle. Shorter leaves support it near the region of greatest bending moment. The stack shares load while allowing each leaf to flex. Contact between leaves creates friction. That friction can dissipate some motion, giving the spring a degree of self-damping. It can also produce squeaks, wear, heat, and resistance to small movements. Lubrication, liners, wrappers, clips, and surface finishing became part of carriage spring maintenance. In 1804, the British inventor Obadiah Elliott patented an elliptic spring arrangement for carriages. Two curved leaf assemblies faced one another to form an oval or ellipse. The body could be supported directly through these springs, reducing dependence on the heavy separate perch or underframe used in some earlier carriage construction. The arrangement helped make vehicles lighter and changed how carriage bodies were supported. Elliott did not invent elastic suspension or the first steel carriage spring. His elliptic system was a significant architectural improvement in a field already containing several spring forms. The carriage spring had to meet conflicting demands. A soft spring improved isolation on rough roads, but allowed large body movement. A stiff spring controlled movement, but transmitted more shock. The load changed with passengers and luggage. Road impacts could be much larger than static weight. The spring had to remain attached, while its ends moved through arcs. Shackles, eyes, pins, and brackets guided the motion. These joints wore and required lubrication. A broken main leaf could allow the axle or body to shift dangerously. Clips helped keep the leaves aligned. Spring makers learned to shape the stress distribution. A leaf with uniform thickness and width does not necessarily use all its material equally. Tapering the leaves or changing their length can move the spring closer to a more uniform working stress. The concept would later appear in parabolic leaf springs with carefully varying thickness. Carriage springs also made failure visible to ordinary travelers. A cracked leaf changed the ride height. A dry stack squeaked. An overloaded vehicle flattened its springs. A repaired leaf could differ from its mate and leave the body tilted. The spring was no longer a tiny mechanism hidden from everyone but a clockmaker. It had become part of the public experience of motion. Railways would increase the load, speed, and repetition again. Railway vehicles needed springs from their earliest practical years. Iron wheels traveled over iron rails. Joints, uneven track, wheel defects, and changes in load created repeated impacts. Without suspension, those impacts reach the vehicle structure, cargo, passengers, and track. Leaf springs became common beneath locomotives, coaches, and wagons. The axle box moved with the wheel set. The spring connected that movement to the frame. Its deflection spread an impact over time and helped keep wheel loads more even as the track changed beneath the vehicle. A railway spring did more than improve comfort. It influenced adhesion, stability, structural fatigue, and the ability of multiple wheels to share weight. Locomotives with several coupled axles required careful load distribution. Equalizing levers could connect spring reactions so one wheel passing over a low point did not lose too much load, while another carried too much. The suspension became a network rather than a row of independent leaves. Buffers and draw gear used springs to soften the forces between vehicles during coupling and changes in train motion. Some arrangements used coil springs. Others used leaf, volute, rubber, or friction elements. The industrial world found more uses. Spring scales converted load into pointer movement. Safety valves used springs to hold pressure against a seat until force from steam or gas reached a chosen level. Governor mechanisms used springs to oppose centrifugal motion. Textile machines used them to maintain tension. Printing presses, agricultural equipment, switches, and machine tools used springs to return levers and keep parts in contact. Furniture brought the coil spring into homes. Upholstered seats and mattresses had once relied mainly on padding, webbing, straw, hair, or layered materials. Coiled wire springs allowed weight to be supported through repeated elastic movement. Rows of springs could be tied together into a larger structure. Later designs placed individual coils inside fabric pockets so they could move with greater independence. The sleeping surface became another spring system, with its own questions of rate, distribution, noise, durability, and comfort. Industrial demand encouraged specialized spring factories. A blacksmith could still make a replacement leaf for a wagon, but a railway, clock factory, furniture company, or mass-produced machine needed large quantities with controlled dimensions and load. Wire drawing mills supplied consistent diameters. Rolling mills supplied strip. Powered coiling machines replaced much hand winding. Furnaces treated batches. Gauges checked free length, load, and fit. The spring gradually became a catalog component. The catalog spring also changed the way designers thought about stored force. Instead of drawing an entire mechanism around a spring made by one local craftsman, an engineer could specify a load at a height, a rate, a material, and an envelope. The spring maker could then design or select a part to meet those conditions. That shift encouraged springs to spread into machines whose purpose was not obviously spring-driven. Steam safety devices provide one example. A boiler must release pressure before the vessel reaches a dangerous condition. Early safety valves often used a weight on a lever. The weight produced a known closing force on the valve. The arrangement was understandable and visible, but it occupied space and changed behavior if the machine tilted or moved. A spring-loaded valve could provide the closing force in a more compact form. Compressing the spring changed the pressure required to lift the valve. Adjustment created convenience, but it also created responsibility. A careless or unauthorized increase in compression could defeat the protective purpose. Spring-loaded safety valves therefore required controlled settings, locks, inspection, and testing. The spring was not safe merely because it existed. Its material, temperature, corrosion, and calibration mattered. Springs also became measuring elements. In a spring scale, load stretches or compresses an elastic member. A pointer translates that movement into a reading. The scale is useful only if friction remains small, geometry stays consistent, and the spring returns to the same relationship after repeated loads. A scale that reads correctly while loading, but differently while unloading, contains hysteresis, or friction somewhere in the system. A spring that has taken a set changes the zero. Temperature can change both the elastic member and the supporting mechanism. Industrial force measurement led to dynamometers, testing machines, and calibrated proving devices. A spring could be used to test another spring. Pressure gauges used related elastic ideas. A curved or corrugated metal element deformed as internal pressure changed. Linkages enlarged the small motion and moved a pointer across a dial. The sensing element was not always a coil. A curved tube, diaphragm, capsule, or bellows could all act as springs. Their shape converted fluid pressure into controlled mechanical displacement. These instruments allowed operators to observe forces that had previously been inferred from sound, heat, leakage, or failure. A boiler attendant could read pressure. A testing laboratory could compare loads. A factory could inspect springs against specified force, rather than only length and appearance. Stored energy also entered entertainment and domestic life. Clockwork toys used wound springs to walk, turn, ring, or move through simple sequences. Music boxes drove pinned cylinders or discs. Spring motors powered phonographs where electricity was unavailable. Cameras used springs to operate shutters, advance film, and return levers. Kitchen timers held a winding and released it through a regulated train. A spring-powered mechanism separates the moment of supplying energy from the moment of using it. The hand winds now, the machine works later. This makes the spring a mechanical reservoir. The reservoir has limits. Winding torque may rise sharply. A stop must prevent damage. A governor or escapement may be needed to control release. Lubricant in the spring barrel can reduce friction, but may also thicken with age. A broken inner or outer attachment can release the spring suddenly inside its housing. Factories making clocks, instruments, toys, telephones, typewriters, and office machines required enormous numbers of small springs. A typewriter key needed to return. A carriage mechanism needed tension. A bell needed a hammer to move and recover. A telegraph relay required contact pressure. A telephone switchboard contained springs that guided plugs, contacts, and indicators. The springs were inexpensive compared with the complete machine, yet one weak or misplaced part could make an otherwise finished product unreliable. This encouraged gauges, sorting, standardized wire, and automatic coiling. It also encouraged engineers to think of springs as functional families. Some stored energy, some maintained contact, some returned a part, some measured force, some isolated vibration. The same physical behavior served very different purposes because the surrounding mechanism controlled how the movement was used. This transition required classification. A spring could no longer be described only as strong or weak. It had a material, wire diameter, coil diameter, number of active coils, free length, installed length, solid height, end form, rate, load range, direction of winding, and expected cycle life. The most familiar modern form is the helical compression spring. It looks like a wire wrapped around an imaginary cylinder. Place it between two surfaces and press them together. The spring shortens and pushes back. The visible motion is axial, along the center line of the coil. The stress in the wire is less intuitive. Most of the wire is not simply being compressed lengthwise. The axial load creates torque in the helical wire. The wire works mainly in torsion. Each active coil twists slightly. Add those small twists around the helix, and the spring shortens by a visible amount. This is one of the quiet, geometric tricks of machine design. A long length of wire can be packaged into a short cylinder, and the torsional flexibility of that wire becomes axial movement. Several dimensions control the rate. Thicker wire makes the spring much stiffer. For an ordinary cylindrical helical spring, rate changes roughly with the fourth power of wire diameter. A modest increase in diameter can therefore produce a large change in force. A larger mean coil diameter makes the spring softer because the load acts through a larger twisting lever arm. More active coils make it softer because more wire shares the total deflection. Fewer active coils make it stiffer. The material's shear modulus also matters. Two springs with identical geometry can have different rates if their materials resist shear differently, though common steels have broadly similar elastic moduli compared with the much larger differences in their strength and temperature capability. The distinction between modulus and strength is important again. A high-strength steel spring is not necessarily much stiffer than an ordinary steel spring of the same geometry. It can often operate at higher stress without taking a set or failing early. The ends determine how the spring meets its supports. An open end follows the helix to its final point. A closed end reduces the gap between the last coil and its neighbor. A ground end provides a flatter bearing surface. Closed and ground ends help a compression spring stand squarely and distribute load, but grinding removes material and introduces heat that must be controlled. Not every coil contributes equally to deflection. End coils constrained against the seat are less active than the free coils in the center. The spring's free length is its length without external load. Its installed length is the length after assembly. Its solid height is the approximate length when all coils have come into contact. Operating a spring to solid height can create high impact, surface damage, and stress. Some designs intentionally tolerate occasional solid contact. Others require a clear safety margin. A compression spring can also buckle. A short, wide spring remains stable between flat seats. A long, slender spring may bow sideways before reaching its intended axial deflection. A guide rod, surrounding tube, larger coil diameter, shorter free length, or different arrangement can control buckling. The guide introduces rubbing and clearance questions. A spring that scrapes continuously against a rod or bore can wear through its protective surface and develop a fatigue crack. Compression springs may be cylindrical, conical, barrel-shaped, or hourglass-shaped. A conical spring can nest its coils as it compresses, producing a low, solid height. As coils contact and become inactive, the rate can rise progressively. Barrel and hourglass forms can improve stability or fit around surrounding components. Variable pitch changes the spacing between coils, closely spaced coils touch first, reducing the number of active coils and increasing the rate later in the stroke. An extension spring works in the opposite visible direction. Pull its ends apart, and it resists lengthening. Many extension springs are wound with initial tension. The coils press against one another, even when no outside load is applied. A certain force must be reached before the body begins opening visibly. Initial tension keeps parts together and removes slack. The hooks or loops at the ends are often the most highly stressed and failure-prone regions. A perfect spring body is of little value if an abrupt hook radius concentrates stress or if the end rubs against its attachment. Machine designers sometimes use separate threaded plugs, swivel hooks, or extended loops so the connection can be replaced or aligned more safely. A torsion spring is usually a helical coil with arms extending from one or both ends. Rotating the arms relative to one another causes the coil to wind tighter or unwind. Despite its name, the wire in a helical torsion spring works primarily in bending rather than in the same torsional mode that dominates a compression spring. The direction of loading matters. Torsion springs are generally arranged so the operating torque tends to wind the coil tighter. Loading in the opposite direction can enlarge the coil and create less favorable stresses or support conditions. Clothespins, hinges, latches, clips, and many return mechanisms use this form. A spiral spring uses a flat strip wound in a plane. The mainspring and balance spring belong to this broad family, though their geometry and duties differ greatly. A torsion bar stores energy by twisting a long straight bar. One end is anchored. The other connects to a lever or suspension arm. The bar may look unlike a spring because it has no coils. Mechanically, it is one. By this point, the spring family has expanded far beyond one shape. The common thread is controlled elastic deformation. The growing automobile industry would place several of these forms beneath a machine exposed to speed, shock, changing load, and continuous public scrutiny. Early automobiles inherited much of their suspension from carriages. Leaf springs supported axles or bodies in familiar arrangements. They were rugged, relatively simple, and capable of locating an axle as well as supporting weight. A semi-elliptic leaf spring, fixed near its ends and attached to the axle near the center, could transmit braking and driving forces in addition to vertical load. That combination reduced the number of separate links required. It also forced one component to perform several jobs. The leaves bent vertically, twisted as the axle moved unevenly, and reacted to acceleration. Interleaf friction affected ride. The spring eyes and shackles wore. The axle seat concentrated load near the center. As vehicles became faster, ride and wheel control demanded more refined systems. Coil springs separated the springing function from axle location. Control arms, radius rods, trailing links, or other members guided the wheel, while the coil carried vertical load. A coil can be compact and low in friction. It does not locate an axle by itself. Torsion bars offered another packaging option. A long bar could run along or across the vehicle, with a lever at the suspension arm. Adjusting the anchor position could change ride height without replacing the bar. All three forms could be designed to provide similar wheel rates. Their space, mass, friction, durability, and control arrangements differed. The wheel rate is not always the same as the spring's own rate. Levers and suspension geometry create a motion ratio. If the spring moves less than the wheel, its required rate must account for that relationship. The angle of the spring changes the effective force at the wheel. A designer cannot choose a coil from vehicle weight alone. The distribution of weight, available travel, desired ride frequency, tire stiffness, unsprung mass, roll control, and damping all matter. When a wheel rises over a bump, the spring compresses and stores energy. After the wheel passes, the spring returns that energy. Without damping, the body and wheel continue oscillating. Hydraulic shock absorbers became essential partners. Fluid forced through valves turns motion into heat. Compression and rebound can receive different damping. Modern dampers may change their valves electronically or respond to velocity through layered valve discs. The spring supports. The damper controls the rate of motion. An anti-roll bar is another torsion spring. It connects the left and right suspension. When both wheels move together, the bar may rotate with little twist. When one side rises relative to the other, the bar twists and resists body roll. The component distributes spring effect according to the relationship between the two wheels. Progressive bump stops add another spring near the end of travel. Rubber, or microcellular polyurethane, compresses increasingly as the suspension approaches its limit. The mainspring, anti-roll bar, tire, seat cushion, bushings, and bump stop all contribute some elasticity. A vehicle is not supported by one spring rate but by a layered system. Failures reveal that system. A broken coil can lower one corner and leave a sharp end near a tire. A cracked leaf changes axle location. A seized shackle prevents normal movement. A weak spring alters ride height and suspension alignment. A failed damper makes a sound spring appear inadequate because oscillation is no longer controlled. Road salt creates corrosion pits, especially where a protective coating is damaged. The pits become fatigue origins under repeated bending or torsion. A spring can survive countless small bumps and then break on an ordinary road because the crack has been growing invisibly for years. Vehicle suspension made spring fatigue familiar to millions of users. Inside the engine, another spring faced a more severe rhythm. It had to open and close a valve thousands of times each minute, follow an accelerating mechanism, and avoid oscillating in ways that the camshaft never commanded. An engine valve spring is compressed between the cylinder head and a retainer attached to the valve stem. When the cam and follower push the valve open, the spring compresses further. As the cam lobe turns away, the spring closes the valve and keeps the follower in contact with the cam profile. At low speed, the motion appears straightforward. At high speed, every part has mass. The valve, retainer, locks, spring coils, follower, and portions of the operating mechanism must accelerate and decelerate rapidly. The spring force must be high enough to control them. Too little force allows the follower to lose contact, the valve to float, or the closing event to become uncertain. Too much force increases friction, wear, stress, and the load carried by the cam, follower, stem, and bearings. The spring itself does not move as one perfectly uniform object. A disturbance travels along the wire as a stress wave. One region can compress while another expands. At certain engine speeds, the forcing from the valve motion can align with one of the spring's natural vibration modes. The coils surge. Some regions move more than intended. Adjacent coils may approach or strike. Dynamic stress rises far above the simple static calculation. Engineers recognized this problem during the early development of high-speed valve trains. Patents and technical papers from the early 20th century described variable coil spacing, changing diameters, dampers, and multiple springs intended to disrupt resonance. A variable pitch spring does not have one perfectly repeated spacing from end to end. Different regions tend to respond at different frequencies. Coils may close progressively, changing the active length. A conical or beehive spring changes coil diameter and mass distribution. A smaller retainer can reduce moving mass. Dual springs place one spring inside another. They can provide redundancy and alter the combined dynamic response. Light interference between them may add damping, though it also creates rubbing and heat. A flat damper spring can fit between coils to control vibration in some designs. The valve spring operates in heat and oil mist. It may experience tens or hundreds of millions of cycles over an engine's life. Surface quality becomes critical. A scratch left by handling can become a crack. Decarburization during heat treatment can leave a softer surface. Corrosion can attack a spring during storage or service. Excessive temperature can reduce strength and cause relaxation. A valve spring may fail by breaking, but it can also lose load gradually. The engine may show reduced control at high speed before any coil separates. Testing, therefore, includes load at specified heights, free length, squareness, surface condition, material properties, and fatigue behavior. The spring must match the cam profile, valve mass, engine speed, installed height, and available clearance. Changing one part without considering the others can move the system closer to coil bind, resonance, or excessive stress. The valve spring is a reminder that a static force deflection curve tells only part of the story. A spring lives in time. The dynamic behavior of a spring can be understood more broadly by pairing it with a mass. Move the mass away from equilibrium and release it. The spring accelerates it back. Momentum carries it through the center. The spring then acts in the opposite direction. The system oscillates. Every mass and spring system has one or more natural frequencies determined by stiffness, mass, and geometry. Add mass and the motion generally becomes slower. Increase stiffness and it generally becomes faster. Add damping and the oscillation dies away more quickly. This simple relationship connects a watch balance, a vehicle body, an engine valve, a machine mount, and a tall building. The scale and details change. The logic remains. When an outside force repeats near a natural frequency, resonance can amplify movement. The forcing itself may be small. Repetition adds energy at the right phase. A washing machine with an uneven load, a reciprocating engine, a fan with imbalance, or a stamping press can excite the structure supporting it. Springs placed beneath the machine may isolate vibration at suitable frequencies. Near the isolation system's own resonance, they can make movement larger instead. This is why soft mounts are not chosen by softness alone. The supported mass, operating speed, start-up and shut-down range, damping, center of gravity, and allowed motion all matter. A machine may pass through resonance briefly while accelerating. If it remains there, movement can become unacceptable. Rubber mounts combine spring and damping. Steel coils may be paired with viscous dampers. Air mounts can provide low natural frequency and automatic leveling. Wire rope isolators use stranded metal cable bent into loops, combining elasticity with internal friction. Shock isolation presents another condition. A dropped instrument or moving vehicle experiences a short input containing many frequencies. A spring increases the stopping distance and reduces peak force, but it must provide enough travel. If it reaches a hard stop, the remaining energy is transmitted abruptly. Packaging foam, seat cushions, suspension bump stops, and industrial shock mounts all manage the relationship between force and travel. The most useful spring response may be strongly nonlinear. Springs can be combined in parallel or series. Place two compression springs side by side under one plate and both carry load. Their rates add. The assembly becomes stiffer. Place one spring after another so the same force passes through both and their deflections add. The combined rate becomes lower than either arrangement in parallel. Real mechanisms add levers, cams, linkages, and changing angles, allowing a constant rate spring to create a changing force at the working point. A designer may also oppose one spring with another. The pair centers a lever or shaft. Preload keeps both springs engaged, so the mechanism has no loose region around the middle. In precision instruments, flexures can be arranged symmetrically, so unwanted motion cancels. In suspension, several springs can share load with bump stops entering only near the end of travel. In valves, a pneumatic force may oppose a coil spring. The system's rate is therefore not always visible from one component. This matters during troubleshooting. A machine that feels too stiff may contain a seized pivot rather than the wrong spring. A mechanism that does not return may be obstructed, corroded, or poorly lubricated. A door that slams may have an intact spring and a failed damper. A vibrating machine may have a broken mount or simply be operating near resonance. The spring participates in motion, but it does not act alone. Engineers learn to calculate these dynamic relationships, then confirm them through testing. High-speed cameras, displacement sensors, strain gauges, accelerometers, and frequency analysis made spring motion visible in ways that slow hand testing could not. A valve spring that appears as a blurred cylinder can be observed coil by coil. A suspension can be measured as the wheel follows a road input. A tiny contact spring can be cycled until its force begins to drift. The spring moved from a static object on a drawing to a dynamic element whose behavior depends on time. In every case, mass, frequency, damping, and repeated stress can matter as much as the load measured while the machine is stopped. By the 20th century, designers understood many of these demands. The remaining challenge was to manufacture springs so that millions of apparently simple coils could meet them consistently. Before a spring is manufactured, its specification must describe what the machine actually needs. A drawing that gives only outside diameter and free length leaves too much unanswered. The useful requirement may be a force at two installed positions. One position represents assembly. The other represents maximum travel. Together they define the working rate more clearly than appearance alone. The designer checks that the spring fits at free length, at installed length, and at its shortest operating length. Clearance is needed around the outside or inside if a guide is present. The ends must meet their seats without interference. Coils must remain apart by a safe amount if solid contact is not intended. The required force includes tolerances. Wire diameter varies slightly. Coil diameter varies. The number of active turns and end behavior vary. Heat treatment and presetting change dimensions. Because helical spring rate is highly sensitive to wire diameter and coil diameter, small manufacturing changes can produce a noticeable load difference. A realistic drawing, therefore, allows variation that the machine can tolerate while controlling the characteristics that matter most. Excessively tight tolerances raise cost without improving function. Loose tolerances can create a machine that works differently from one assembly to the next. The environment is part of the specification. A spring operating in clean indoor air has different needs from one exposed to salt spray, steam, fuel, vacuum, food product, or furnace heat. A coating that survives storage may not survive coil contact. A stainless grade that resists water may be attacked by another chemical. A polymer guide compatible with one lubricant may swell in another. The consequence of failure also changes the design. A spring returning a pen button can be inexpensive and easily replaced. A spring holding a critical valve closed may require traceable material, controlled surfaces, redundant arrangements, and extensive fatigue testing. Some mechanisms are designed so a broken spring moves the system toward a safer state. Others use two springs so one can retain partial function. Dual valve springs can provide dynamic benefits and limited redundancy. A pair of extension springs on a door can share load, though their attachments must also be capable of containing a failure. The surrounding structure must withstand the stored energy. A spring under preload continues pushing during disassembly. Retainers, covers, and tools may hold considerable force even when the machine is switched off. Service procedures release or restrain that energy in a controlled sequence. This is especially important with large suspension springs, industrial dies, accumulators, and spring-loaded valves. The spring does not become harmless because motion has stopped. Designers also consider what happens at the boundaries of travel. A compression spring may need a stop that prevents overload. The stop must engage before the spring reaches damaging stress, but not so early that useful movement is lost. A torsion spring arm may need a support that avoids concentrating force at one sharp edge. An extension spring may need a safety cable through its center so a broken piece remains contained. Noise can become a specification. Coil contact, seat movement, interleaf friction, and resonance create sound. Plastic sleeves, shaped seats, variable pitch, surface coatings, or damping materials can reduce it. Each treatment changes friction, heat, corrosion, or space. The spring's orientation may matter. Gravity can make a long spring sag. Centrifugal force can change the behavior of a spring rotating with a shaft. A spring operating horizontally may rub a guide differently from one standing vertically. The final design is a compromise among force, movement, life, space, mass, cost, environment, noise, and service. Only after that compromise has been defined does the factory begin turning wire or strip into the required elastic shape. Spring manufacture begins before the wire reaches the coiling machine. The steelmaker controls composition and cleanliness. The rod mill controls the starting size and internal condition. Wire drawing reduces the diameter through a sequence of dies, improving dimensional consistency while changing the material through cold work. A spring factory receives wire or strip selected for a particular duty. High-carbon music wire is widely used for small, highly stressed springs operating at moderate temperature. Oil-tempered wire offers useful toughness and is common in many industrial and automotive springs. Chrome silicon and chrome vanadium steels serve demanding fatigue, shock, and temperature conditions. Stainless steels resist corrosion in selected environments. Phosphor bronze, beryllium copper, and other copper alloys provide electrical conductivity, corrosion resistance, or non-magnetic behavior. Nickel-based alloys retain useful properties where ordinary spring steel would relax or oxidize too quickly. No material is best everywhere. Music wire can provide excellent strength, but may be unsuitable for corrosion or high heat. Stainless steel may resist rust, while offering different fatigue, magnetic, or cost characteristics. A nickel alloy may survive a turbine or furnace instrument, but be unnecessary in a household latch. The manufacturing route also depends on size. Small and medium springs are commonly cold-coiled. Wire at room temperature is fed through guides into a machine. Coiling tools bend it around a point or mandrel, while feed rollers control length. The machine determines coil diameter, pitch, number of turns, and end geometry. Modern computer-controlled spring coilers can change pitch and diameter during the same part. They can form hooks, legs, or variable shapes without removing the wire from the machine. The wire springs back slightly after leaving the tooling. The machine setup must anticipate that recovery. Different heats of material, wire diameters, and temperatures can change springback. To speak too loudly, the operator or control system adjusts the process so the finished coil reaches its intended size after the tooling force disappears. Large springs may be hot-coiled. A heavy steel bar is heated until it can be formed without cracking or requiring impossible force. It is wrapped around a mandrel, then heat-treated to establish the required structure and strength. Hot coiling makes massive railway, mining, heavy vehicle, and industrial springs possible. It also introduces scale, decarburization, distortion, and the need for controlled quenching and tempering. Leaf springs begin as flat bar or tapered sections. The leaves are cut, holes and eyes are formed, and the steel is heated or cold-worked according to the process. The main leaf may have rolled or wrapped eyes at its ends. Individual leaves are cambered so the assembled pack assumes the required curve. A center bolt or related fastener aligns the stack. Clips control lateral movement while allowing flex. Bushings in the eyes provide a replaceable interface with pins or shackles. The heat treatment stage determines whether the shaped steel behaves like a spring or like a piece of bent bar. For many spring steels, the material is heated into a range where its internal structure changes, then quenched to create high hardness and strength. Tempering follows to reduce brittleness and establish the desired properties. The exact temperatures, times, and cooling methods depend on the alloy, section size, and part. A small wire spring may receive a stress relief treatment after cold coiling rather than a full harden and temper cycle at the spring factory. The incoming wire may already possess most of its strength through drawing and prior treatment. Cold coiling leaves residual stresses from bending the wire into shape. Stress relief helps stabilize dimensions and improve performance. Heat must be controlled carefully. Excessive temperature can reduce strength. An oxidizing furnace atmosphere can remove carbon from the surface. That decarburized layer is especially damaging because spring fatigue cracks often begin at the surface, where operating stress is high. Protective atmospheres, coatings, rapid processing, and later surface removal can reduce the problem. Compression spring ends may be ground after coiling and heat treatment. The spring stands against a rotating abrasive wheel or passes through a double-end grinding machine. Material is removed until the ends are sufficiently flat and parallel. Grinding helps the load enter evenly, but it can create burns, sharp edges, or local damage if pressure and cooling are poor. The spring is then deburred and cleaned. One of the most important 20th century improvements in fatigue performance is shot peening. A stream of small steel, ceramic, or other controlled media strikes the spring surface. Each impact creates a tiny plastic indentation. Beneath the visible surface, the surrounding material is left with compressive residual stress. Fatigue cracks generally open under tensile stress. A compressive surface layer means the operating tensile stress must first overcome that beneficial compression before a crack can open and grow. Shot peening does not make the material invulnerable. Coverage, intensity, media condition, and access must be controlled. A region hidden from the shot may receive less benefit. Broken or contaminated media can damage the surface. Peening cannot repair a deep seam, poor heat treatment, or incorrect design. When performed correctly, it can greatly improve the fatigue resistance of highly stressed springs. Valve springs, suspension springs, and other dynamic components often receive carefully specified peening. Some springs are preset, also called scragged or set removed. A compression spring is compressed beyond its intended maximum operating position, sometimes close to solid height, under controlled conditions. The most highly stressed regions yield slightly. After release, the spring becomes shorter than it was before the operation and develops residual stresses that can improve stability and usable stress range. The customer receives a spring that has already experienced much of the initial permanent set that might otherwise occur in service. Presetting must be designed into the part. Compressing an arbitrary spring until it yields is not a substitute for correct manufacture. Extension and torsion springs may receive analogous setting operations appropriate to their motion. Surface finishing follows the environment. Oil or phosphate coatings provide temporary corrosion protection and help during handling. Paint, powder coating, or epoxy can protect suspension springs. Zinc and other metallic coatings provide corrosion resistance in selected uses. Stainless material may need passivation. Plating high-strength steel creates a serious concern. Acid cleaning and electroplating can introduce atomic hydrogen into the metal. The hydrogen can move toward regions of high stress and reduce ductility, causing delayed brittle fracture. A spring may pass inspection and break hours or days later without obvious overload. Processes for high-strength springs therefore control cleaning, coating, and prompt baking intended to remove diffusible hydrogen. Alternative coatings may be chosen when risk is unacceptable. Coating can also change dimensions and contact. A thick layer on a close-fitting spring may crack or rub away. Coils that contact one another can damage paint. A coating may protect the outside while leaving the ground ends exposed. Design and finishing remain connected. Manufacturing is followed by inspection. Free length is easy to see, but it is not enough. A compression spring may be tested at one or more specified heights. The machine compresses it and records the force. From those points, the rate and load agreement can be evaluated. A torsion spring is checked through angle and torque. An extension spring is tested for initial tension and load at length. A leaf spring is loaded through a fixture that represents its supports. Dimensions include wire diameter, outside or inside coil diameter, pitch, body length, end orientation, squareness, and parallelism. A spring can have the correct free length and the wrong rate. It can have the correct rate and the wrong solid height. It can meet both while leaning far enough to rub inside its housing. Dynamic testing is required when cycle life matters. Test machines compress, extend, bend, or twist springs repeatedly while controlling load, stroke, temperature, and frequency. A sample may run for millions of cycles. Failures are recorded by location and life. The test can compare material, peening, heat treatment, or geometry. No laboratory test reproduces every field condition. Road salt, grit, misalignment, random shock, and temperature variation may create combinations difficult to accelerate faithfully. Testing still reveals process drift and provides a rational basis for design. Non-destructive inspection may look for surface cracks through magnetic particle or penetrant methods. Hardness measurements verify treatment. Metallographic samples reveal decarburization, grain structure, case condition, and inclusions. Residual stress and peening checks support critical production. The factory also controls variation statistically. Wire diameter changes slightly along a coil. Tooling wears. Furnace temperature drifts. Grinding wheels change condition. If measurements are considered only after parts exceed the drawing limit, the process has already lost stability. Control charts and sampling reveal trends earlier. Standards and shared terminology allowed these measurements to travel between companies. A customer could specify material, direction of coiling, end form, loads at stated heights, permissible dimensions, surface treatment, and test requirements. The spring maker could interpret those requirements without reproducing the customer's entire machine. Standardization did not make every spring interchangeable. Two coils with the same outside diameter and free length may have different wire, active turns, rate, fatigue life, temperature capability, and end condition. A spring that fits physically can still be functionally wrong. Catalog parts made ordinary mechanisms economical, while custom springs remained necessary where force curves, space, life, or environment were unusual. The drawing became a contract between machine behavior and manufacturing capability. It translated a moving requirement into dimensions and loads that could be inspected while the spring sat still on a bench. That translation is one of the less visible achievements of industrial spring making. The part remains simple enough to recognize at a glance, yet its useful identity lies in numbers that cannot be judged by sight alone. The apparently simple spring is therefore produced through a chain of decisions. Material is selected, wire or strip is formed. Residual stress is managed. Heat treatment builds strength. Ends and surfaces are finished. The part is preset, protected, measured, and cycled. The goal is not merely to make a shape that pushes back once. The goal is to make its 10,000th or millionth movement resemble its first. Even a well-made spring can fail when its environment, installation, or loading differs from the design. The fracture surface and the shape left behind often reveal which limit was crossed. A spring that has taken a permanent set usually experiences stress, temperature, or time beyond its ability to recover. The coils may remain intact, but the free length changes. A vehicle sits lower. A valve spring produces less installed force. A seal face receives less pressure. One severe overload can cause set immediately. Lower stress at high temperature can cause relaxation gradually. The material's internal structure moves slowly toward a state that carries less stress at the same deflection. Creep and stress relaxation are related but described from different conditions. In creep, strain increases under a sustained load. In stress relaxation, force decreases while the part is held at a fixed position. Polymers and elastomers show these effects strongly, but metals also relax when temperature and stress are high enough. Fatigue produces a different history. The spring may operate well below the force required to break it in one pull. Repeated stress starts a small crack, commonly at the surface. Each cycle advances the crack by an almost invisible amount. The remaining section carries more stress until final fracture occurs. A fatigue fracture often contains a relatively smooth region where the crack grew, and a rougher final region where the remaining material failed suddenly. The origin may be a tool mark, corrosion pit, seam in the wire, grinding burn, decarburized area, or contact scar. Spring design uses stress range as well as maximum stress. A spring cycling between two compressed positions experiences a mean stress and an alternating stress. Preload can raise the mean while reducing the chance of separation. The acceptable combination depends on material, surface, life target, and reliability. A spring used only a few times can operate nearer its static limit than one expected to cycle continuously for years. Corrosion fatigue is especially destructive. A pit concentrates stress and continues growing in a moist or salty environment. Protective coatings are damaged by stones, coil contact, or handling. Rust forms beneath an apparently small chip. Suspension springs often break near lower seats, where water and debris collect. The location reflects environment and contact as much as the nominal stress calculation. Fretting occurs where a spring rubs through small, repeated movement against a seat, guide, or neighboring coil. The surface becomes polished, oxidized, and damaged. The wear mark can become a crack origin. Coil bind creates high contact and impact when adjacent coils close completely. A spring compressed beyond the intended travel may not have space for wire tolerances, dynamic overshoot, or deflection of the surrounding structure. Buckling changes the load from controlled axial torsion into bending and rubbing. A long compression spring can bow until one side contacts a guide or housing. Misalignment loads one edge of the end coil. A seat that is not square makes the spring lean. An extension spring pulled sideways twists its hooks. A torsion spring mounted on the wrong arbor diameter changes clearance and stress. Resonance creates dynamic stress beyond the static load. A spring can appear acceptable during slow testing and surge violently at operating speed. Temperature changes both dimensions and material strength. Cold can reduce toughness in some materials and make polymers stiff. Heat lowers modulus slightly, accelerates relaxation, changes coatings, and can expose the spring to oxidation. Hydrogen embrittlement produces delayed fracture, with little plastic deformation. It is particularly dangerous because the spring can break while sitting under assembly load rather than during a visible overload event. Diagnosis requires the full system. Replacing a broken spring with an identical part may lead to another failure if the seat is misaligned, the damper is seized, the environment is corrosive, or the mechanism reaches an unintended stop. A fracture near one end may point toward seating or surface damage. Several broken coils in similar positions across a fleet may reveal a design stress or manufacturing issue. Random failures after plating may raise concern about hydrogen. Loss of force without fracture may suggest relaxation or set. The spring should not be blamed merely because it is the part that broke. It may have absorbed loads created elsewhere. A valve spring suffers if the cam profile, retainer mass, or engine speed changes. A suspension spring suffers if a damper fails and allows repeated full travel. A seal spring corrodes if the process fluid reaches a material not selected for it. A switch spring overheats if electrical contact resistance rises. Failure analysis returns the spring to its real role. It is a controlled elastic member inside a larger machine. The helical coil became common because it packages a long elastic member efficiently. It is not the answer to every spring problem. Some machines need very large force through very little movement. Others need long travel in a thin housing. Some require a nearly constant pull. Some cannot allow an ordinary coil to reach solid height. The spring family developed specialized shapes for these conditions. The disc spring is one of the most compact. It resembles a shallow conical washer. Press its center and outer rim toward the same plane, and the disc changes shape while resisting the load. The form is associated with the French engineer Julien Belleville and is often called a Belleville spring or Belleville washer. Historical accounts disagree over the precise patent year in the 1860s, so the name is more secure than a dramatic claim of one exact beginning. A single disc can carry a large axial load through short travel. Discs can be stacked. Place several in the same orientation, and their load capacity combines while travel remains relatively short. Alternate their directions, and the stack gains movement while carrying about the load of one disc. Mixed arrangements can create a chosen combination of load and deflection. Friction between discs affects the response. Edges and support diameters matter. Excessive flattening can create high stress. A stack that looks like a group of washers is actually a designed spring system. Disc springs appear in clutches, valves, bolted joints, tooling, overload devices, and mechanisms where axial space is limited. Their use beside bolts creates an early glimpse of the next episode. A disc spring can help maintain clamp load as temperature changes or surfaces settle. It still needs a threaded fastener or another structure to hold the assembly together. A volute spring is formed from a tapered strip wound into a cone or spiral that can telescope into itself. As it compresses, the coils slide over one another. The form can carry heavy load and collapse into a short space. Sliding friction provides damping, which may be useful in buffers and heavy shock applications. The same friction creates heat and wear. Lubrication and surface finish influence behavior. A wave spring is made from flat wire or thin strip formed into waves around a circle. The waves flatten under axial load. Several turns can be stacked or formed as one continuous coil. Wave springs fit where an ordinary round wire compression spring would require more axial height. They maintain preload in bearings, seals, connectors, and compact assemblies. Their edges, wave count, contact points, and manufacturing accuracy affect load. They are not simply flattened coil springs. A constant force spring is usually a pre-stressed strip wound tightly onto a drum. Pull the free end and the strip uncoils. Over a useful range, the force remains approximately constant because the strip moves between its tightly curved stored shape and a straighter working shape. The force is not perfectly constant from the first fraction of movement to the end. Drum diameter, strip thickness, residual stress, and mounting affect it. Tape measures use a related coiled strip behavior. Retractors, counterbalances, window mechanisms, electrical cords, and access panels use constant force springs when a long stroke is required, without the steadily rising force of an ordinary extension spring. A negator motor uses one or more pre-stressed strips to deliver rotational energy from a compact package. Such devices appeared in instruments, timers, and mechanisms requiring a relatively even torque. The clock mainspring remains a power spring, but modern spiral power springs can be designed with different cross-sections, attachments, and housing arrangements. Some operate inside lubricated barrels. Others are dry. Their strip edges must remain smooth, and the coils must avoid damaging contact as they wind and unwind. A flat spiral spring can also produce a restoring torque rather than power a complete mechanism. Electrical meters once used delicate hairsprings to control pointers. The spring both returned the pointer and, in some designs, carried current into a moving coil. The material had to be elastic, conductive, stable, and resistant to magnetic or temperature effects. Contact springs form another broad family. A bent strip of copper alloy can press two electrical surfaces together, return a key, hold a battery, or provide a wiping action that breaks through light contamination. The spring carries both mechanical and electrical requirements. Higher force may reduce contact resistance but increase wear and operating effort. Lower force may permit vibration or oxide films to interrupt current. Heating from resistance can relax the spring and make the contact worse, creating a feedback loop. Phosphor bronze and beryllium copper became important because they combine useful spring properties with electrical conductivity and corrosion resistance. Stainless and nickel alloys serve other environments. A clock hairspring, a relay contact, and a vehicle leaf spring are all elastic members, but the important material property is not the same in each. Scale changes the problem. At small dimensions, surface condition, plating thickness, and contact forces can dominate. At large dimensions, heat treatment through the section, mass, and impact become central. At extremely small scales, machines can make springs without coiling wire at all. Micro-electromechanical systems, often called MEMS, contain beams and flexures patterned into silicon or thin films. A microscopic proof mass can move on these elastic supports inside an accelerometer. Motion changes capacitance or another electrical signal. The spring may be a folded beam, only a tiny fraction of a millimeter wide, created through lithography and etching rather than winding. Its underlying function remains familiar. It allows controlled movement and produces a restoring force. Flexures offer motion without sliding joints. A thin region bends while the surrounding structure remains relatively rigid. Precision instruments use larger flexure hinges for the same reason. With no pin, bushing, or lubricant at the joint, backlash and friction can be extremely low. Travel is limited, and stress concentrates in the flexible region. The geometry must be designed so the material remains elastic through the required motion. Some spring forms deliberately combine elasticity and friction. Others attempt to remove friction almost entirely. The variety reflects the larger truth of spring design. The useful part is not the coil. The useful part is the controlled relationship between force and movement. Metal springs dominate many machines, but they are not the only way to store mechanical energy. Compressed gas behaves like a spring. Reduce the volume of a sealed gas, and its pressure rises. Allow it to expand, and it can push a piston or flexible wall back. An air spring in a vehicle often uses a reinforced rubber bellows filled with compressed air. The air carries the load. The bellows contains it and guides the change in volume. Changing pressure can alter ride height and effective rate. Connecting the spring to an additional reservoir changes the volume available and therefore the response. Valves, compressors, dryers, sensors, and control systems turn the air spring into part of a pneumatic network. The gas response is naturally progressive because pressure rises as volume decreases. Heat transfer also matters. Rapid compression warms the gas. Slow movement allows more heat exchange with the surroundings. The apparent spring behavior can therefore depend on speed. An air spring is not automatically a damper. Some pneumatic systems contain restrictions that dissipate energy, but vehicle suspensions commonly use separate hydraulic dampers. A gas spring is another device. A pressurized cylinder contains a piston and rod. Gas pressure, acting over the effective piston area, produces an extending force. Oil may provide end-of-stroke damping and lubricate seals. Gas springs support hatchbacks, machine guards, chairs, hospital equipment, and adjustable furniture. Their force changes with stroke, temperature, internal friction, and gas pressure. A cold gas spring may feel weaker. A damaged seal allows pressure to escape. The device may still look intact while its support force fades. The rod surface is part of the seal system. Scratches and corrosion shorten life. Mounting orientation can influence lubrication and damping in some designs. Elastomer springs store energy through deformation of rubber or related polymers. Rubber can work in compression, shear, tension, or combined modes. Engine mounts, suspension bushings, vibration isolators, couplings, and bump stops use it. Unlike an ideal metal spring, an elastomer shows substantial hysteresis. The unloading path does not perfectly retrace the loading path. Some energy becomes heat. This built-in damping is valuable for vibration isolation. Its behavior is also sensitive to temperature, time, frequency, chemical exposure, and manufacturing history. Rubber becomes stiffer in the cold, softens with heat, ages through oxidation, and can swell in incompatible fluids. A rubber spring held under compression may develop set. Bonding to metal inserts introduces another possible failure interface. Composite materials offer a modern version of the leaf spring. Glass or carbon fibers embedded in resin can be arranged along the direction of bending stress. A composite leaf can reduce mass and resist ordinary red rust. Its failure behavior differs from steel. Damage may involve matrix cracking, fiber breakage, delamination, impact damage, or degradation at attachments. Inspection and repair methods must match the material rather than assume a steel crack will be visible. Nickel-based spring alloys serve high temperatures and corrosive environments. Their cost is justified when ordinary steel would relax, oxidize, or lose strength too quickly. Cobalt and precipitation-hardened alloys serve still more specialized conditions. Titanium springs can reduce mass and resist corrosion, but material cost, surface behavior, modulus, and manufacturing require careful consideration. Shape memory alloys add a different kind of return. A nickel-titanium spring can be deformed in one state and recover a trained shape when temperature changes its crystal structure. The spring can act as a compact thermal actuator. It is not a universal replacement for steel. Its force, stroke, cycle life, response time, thermal control, and hysteresis suit particular tasks. At the opposite extreme, a spring may be made almost entirely from geometry and pressure. Magnetic fields can provide restoring force in specialized suspensions. Fluid accumulators use compressed gas behind a diaphragm or piston. Flexible diaphragms act as springs while separating media. Corrugated metal bellows combine sealing with axial elasticity. The line between spring and surrounding system becomes less distinct. A bellows may seal, guide, and apply force. An elastomer O-ring may seal and provide a small restoring load. A pressurized chamber may support weight and adjust height. A flexure may guide motion without a bearing. Modern engineering chooses among these forms by asking what must remain stable. Is the key quantity force, position, energy, frequency, height, contact pressure, or vibration isolation? How many cycles are required? What temperature and environment surround the part? What happens if it fails? Can it be inspected or replaced? The modern spring catalog is large because the answer changes from machine to machine. Still, the same physical boundary remains. The part must move far enough to be useful and return closely enough to be trusted. A spring that is too rigid stores little useful movement. One that is too flexible may run out of travel or lose control. A spring stressed too highly becomes a permanent new shape. One stressed modestly but cycled endlessly may fatigue. The long history of springs has been the effort to place that boundary where the machine needs it. Return now to the mechanical seal from the beginning of the story. The rotating shaft is quiet. Two seal faces meet around it. Behind one face, several small springs remain compressed. The springs do not know whether the pump is new or old. They respond only to position, load, temperature, and the condition of their material. As the faces wear by a microscopic amount, the springs extend by a microscopic amount. As pressure or vibration moves the face, they follow. Their force is not the only force in the seal. Hydraulic pressure, bellows stiffness, friction, and geometry all contribute, yet the small coils help preserve contact when the machine passes through changing conditions. That quiet adjustment connects the spring to nearly every chapter we have followed. The ancient bow stored energy through bending. The fibula returned a pin toward its catch. The clock mainspring made a portable mechanism run. The balance spring created a controlled oscillation. Hook gave elasticity a proportional language. Huntsman's crucible steel improved the material available for delicate parts. Carriage and railway springs carried moving weight. Vehicle springs separated the body from the road while dampers calmed the motion. Valve springs followed a cam at speeds high enough for the coils to develop waves of their own. Spring factories learned to control wire, heat treatment, surface stress, set, coating, and fatigue. Disc, wave, volute, constant force, air, gas, rubber, composite, and microscopic springs adapted stored force to different spaces and environments. A spring rarely appears to be the central part of a machine. It is more often the part that keeps another part ready. It keeps a contact closed until a signal arrives. It holds a valve against a seat. It keeps a brush against a commutator, a roller against a cam, a latch inside a notch, or a tensioner against a belt or chain. It supports weight while allowing movement. It waits. If this story brought back the sound of a screen door spring, the feel of an old mattress, a box of small coils in a workshop drawer, or a vehicle that sat lower on one corner, you can leave that memory below when morning comes. The spring's apparent simplicity hides a precise agreement with the machine around it. The seats must be in the right place. The travel must remain within range. The material must survive the environment. The load must be enough, but not too much. The moving parts must remain guided, and the spring itself must be held. A compression spring can press two surfaces together, but without surrounding structure, it simply pushes them apart. A torsion spring can return a lever, but its body and legs need anchors. A leaf spring can support an axle, but eyes, pins, brackets, and a frame must define where the load belongs. A valve spring can close the valve, but retainers and locks must secure it to the stem. Stored force alone does not create an assembly. Machines still need a way to place parts together, clamp them with controlled force, resist vibration, and later allow them to be removed for repair. Permanent joining methods can weld, rivet, braze, or bond. Many machines require something more reversible. They require a helical ramp cut around a shaft or inside a hole, turning rotation into axial movement and clamp force. A spring can apply force. It cannot decide where two machine parts belong, draw them into one structure, and still allow them to be separated with a tool. That problem belongs to the screw and the bolt, and that is where we'll leave the machine tonight. Until our next journey, sleep well.